Okay, instead of ending or before we end in the same lecture, let us see one more example which I felt is very important. Now you can read it, design a Turing machine to recognize all strings in which 010 is present as a substring. It's a very simple question. Imagine you have a tape and a string made up of zeros and ones is stored. What you have to simply find out whether the string has the substring 010. There's a simple strategy. Just start reading the string from left to right, one symbol at a time. The minute you come across the pattern 0, 1, 0, just land into the halt state and declare that the string is accepted. So let's see how the machine has been designed. Initial state Q0. Now look here, the string may start with 0 or it may start with 1. Irrespective of whatever it starts with, whether 0 or 1, we have decided that we will simply keep on reading from left to right, one symbol at a time. So in case if it is 0, keep that 0 as it is and move the tape head towards right. In case if it is ones, keep on reading them and keep on moving towards right. But the minute you come across a pattern 0, then followed by 1, and then again followed by 0, then you need not read anything ahead. You can simply land into the halt state and declare that the string is accepted. Let's see an example. Imagine a string 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, and a blank. So we start reading from here. So we keep the blank as it is and move towards right. The first one we read, we land into the same state Q0. Another we read and just move towards right and land into Q0. Another one we read, we again land back into the state Q0. Then the first time we have come across a 0. We read it and keep it as it is and move towards right. So now where are we? In the state Q1. In the state Q1, we come across with symbol 1. So we read this 1 and move towards right by keeping 1 as it is. Now we are in which state? Q2, and we are at which symbol? 0. Yes, we have come across another 0, and the minute we have the pattern or we found the pattern 0, 1, 0, just read that 0, move towards right. The tape head will be here, but we will land in which state? Halt state. So this remaining part we need not read. So this is how the machine works and accepts a string which is made up of the substring or has a substring 0, 1, 0. Just imagine if you have the string 0, 0, 0 and a blank. So what happens? We start reading this blank and move towards right. This 0 we read and then we move towards the state Q1. In Q1 we read another 0, keep it as it is and land into the same state. We read another 0 and we land into the same state, and now we have reached a blank. Now when you are in Q1, do you find a transition for what to do if you reach a blank? No. So you are just stuck. So this simply means that it has rejected the string, or the string is not of the required type or pattern, and hence if you just leave out this halt with acceptance, all three, that is Q0, Q1, Q2, act as non-accepting states. Okay, now the next example is of a grammar. If you remember, we had learned 4 different types of grammars. Type 0, which is unrestricted grammar. Type 1, context sensitive grammar. Type 2, which is context free grammar. And type 3, which is regular grammar. Today, we are discussing here about unrestricted grammar. The reason is we are learning the unit Turing Machine. Unrestricted grammars produce the recursively enumerable languages, and as we learned, recursively enumerable languages are recognized using Turing machines. So we can look here. If the language L is a recursively enumerable language, then the machine M, which is a Turing machine, will accept it. If the string W belongs to your language, then the machine will halt into the final state or the halt with acceptance. But if the string does not belong to the language, the machine will halt in any one of the non-final states, or sometimes may also loop forever. Now, what is an unrestricted grammar? A grammar is made up of production rules of the type alpha gives rise to beta, or it can be U gives rise to V. What do you have on the LHS? A combination of terminals and non-terminals. So non-terminals are also called as variables. What do you have on the right hand side? You also can have any combination of non-terminals and terminals. So there is no restriction at all. You can have any numbers of symbols on the left as well as on the right, and of any combination. Hence the name unrestricted grammar. This is an example you can see here. S gives rise to ABC, AB gives rise to CA, AC gives rise to D. Here, small a, B, C, and D are the terminal symbols, whereas capital S, B, and A are the non-terminals, or what you call it as the variables. Yes, right. You can also observe an example. A standard grammar is written here for the language A raised to N, B raised to N, C raised to N. And it's an context sensitive language, or you can also call it as recursively enumerable language. Okay. So this is finally, we summarize regular language, context-free language, context-sensitive, recursively language, recursively enumerable languages. We designed DFAs for this, PDAs for this, linear bounded automatas for this, and Turing machines for this. So which is the most powerful machine? Turing machine, which can be designed for recursively enumerable language, context-sensitive language, context-free language, as well as regular language. So thank you, students. We have covered the first part, Turing machine, which works as language acceptor, and very soon we will learn how it computes some input into an output. Thank you once again.